Okay, I think we can continue our discussion about the inorganic membrane preparation. In our previous study, I think last time we talked about the green membrane, what the green means. Okay? Green membrane means incomplete or transition state of the membrane process before the final membrane is called the green membrane, which has some mechanical strength. Okay, some mechanical strength, so that you can handle those green membrane for the final stages, because you need to handle those, the intermediate state of your membrane before the sintering. So green membrane has to have some kind of mechanical strength. Now we can make the inorganic porous membrane by using this green membrane after sintering. Now this is the suspension coating and the Zollgel process, and the next slide is about the Zollgel process itself. Usually when you have organic material and the inorganic material, usually the inorganic material has the reactivity in some cases. For example, we have alkoxide. When we have for methoxide in silicon, the alkoxide is could be easily hydrolyzed to become hydroxide. So this silicon tetraoxide is very reactive. It could become hydrolyzed to become the silicon oxide, so that you can make the Zoll in the alkoxide in the alcohol, and if you put the water, then it will be hydrolyzed to become hydroxide. So alkoxide will become Zoll, of course, and you make a polymer in the solution, so that these will be mixed together, and after casting, you can have separate phases, of course, the polymeric phase and the colloidal phase inside of the membrane. But Zoll will become gel in the case of the colloids. Of course, the starting material is an alkoxide. So after drying, you have inorganic green membrane, and after sintering, you can make the inorganic membranes. Because you start from the low molecular component in the alkoxide, in the Zoll, but after making gel, you can have a SiO connectivity, silicon oxide connectivity in the gel. After hydrolysis. So Zoll will become gel after cross-linking. This is more like a cross-linking reaction. And this was dispersed in the polymeric material. And after drying of your Zoll in the polymeric state, which means that you can evaporate your solvent, then you can make the composite membrane after the sintering. Of course, depending upon the sintering temperature, you can remove most of the hydrogen and the rest of the elements except the carbon. So you can have a carbon and silica composite membrane after sintering at high temperature, above 500 degrees C. But if it's lower than 500 degrees C, you have a polymeric phase, of course, dispersed with the colloidal gel. Next preparation method is about the perovskite membrane. This perovskite membrane has a very high electron conductivity, so it could be used to make the oxygen selective membrane called the ion transport membrane, ITM. Usually this perovskite membrane has several the metallic and oxide structures, and it's not simple, but it has a little bit of a very fine structures. They have a potential to separate the oxygen from air, and oxygen conducting gas mixtures could be used for the membrane reactor at high temperature. Traditional method to make this perovskite powder was to make citrate state, a solid state, or cold precipitation states, and we can take a look at each of us. The citrate stage or solid state, cold precipitation states have a little bit of different stages, but it contains lithium, strontium, cobalt, and ferrous nitrates as a starting material in the case of citrate. But in the case of solid state, we have a little bit of complex components like carbonates or nitrates in the solution as a starting materials. So raw materials are a little different. Processes might be a little different. I do not want you to repeat everything, but you have you can make the gel and gel, and finally after sintering, you can make some type of the perovskite type of membrane containing several of those components. And this component this method was recently been modified in many of the literatures, and so this is one of the method, and it contains very, at least 4 or 5 components in the metallic stages, and it was linked together, and the preparation method is quite different anyway. Well, I'm not an expert, and I'm not intending to specifically ask you to how to make this, but this might be some sort of an art, okay? Depending on the temperature, depending on time, and pressing or unpressing, and sintering temperature, the functionality and the performance of this perovskite membrane was quite different. This year, I have not received any the paper to submit it to Journal of Membrane Science this year, but until last year, there were a lot of submissions, and they can modify. You can change this composition, and can submit it. So it was a little bit of a difficulty to find out the novelty of this method. Anyway, well, next stage is about the zeolite membrane. Zeolite is one of the very typical example of the inorganic membrane. Zeolite means that it has the boiling water. It's a boiling stone. I'm sorry, the boiling stone. So in the Greek letter, it's a boiling water, and perhaps it comes from the water vapor is coming through this the stone. So they thought that this might be a very peculiar stone, but in fact, this zeolite, although it's a very hard material, has a lot of porosity, and it's regarded as a microporous inorganic membrane. And although this is a rock, if you can make and mimic this zeolitic membrane, that's what that means. So in the nature, zeolites could be formed from the volcanic, reactions, volcanic rock of the specific chemical composition immersed in the water to make this kind of zeolitic the rocks. We can make a zeolite in the laboratory scale, and this zeolite has been used as a catalyst in the petrochemical industry. So they use this zeolite in many of the chemical industries so far. But then the membrane community realized that we can use this zeolitic structure, and this zeolitic structure is crystalline. Okay, crystalline. So they have a very fine porous structure because of the crystallinity. Okay? If the crystalline structure means that you have a very, distinct structure rather than randomly oriented amorphous structures, which doesn't have the order. So you have an order in the zeolite structures. Well, this is one of the example of the zeolite membrane called FAU, or Fauxite elementary cells. And it has a silicon, and oxide. Oxide is linked together just like what we have made in here, and through this hole, we can have distinct structures, distinct pore-sized structures in three-dimensional way. So silica is regarded as an inorganic component. Well, oxygen is not, but the silica, the silica is an inorganic material anyway. Now, later, the scientists realized that let's make this zeolitic structure in the laboratory, right? And they can change this silica into some other things. They can change this oxygen to the organics. Okay, you can make organic frame, and inside of the organic frame you can incorporate those inorganic materials. So you can make this zeolitic and imidazolium framework called ZIF, ZIF, or you can make an organic frame and change the metallic structure. Okay, change this silica into the metallic structures and make the metal organic framework, MOF. Depending upon how you can make a framework in the organic structure or the metals, you can change a lot of those numbers, starting from MOF 1. I think right now maybe MOF several hundreds of MOFs has been synthesized and reported in the literatures for the last almost 10, 15 years. And one of the very well-known MOF guy is Professor Yagi at right now Berkeley at the chemistry department. But he was at the UCLA. He's I think Eurodinian. I'm sure Eurodinian. I think he reported many MOFs and started his study publishing in I think 2000, around 2000 in Nature. Right? He published a lot of papers in Nature and Science, not just several, but many of them. Some of them were making some breakthrough in terms of the ability to absorb some gases, or a lot of surface areas, because the surface area is quite different, much larger in this case compared with the non-porous structures. Surface area of the polymeric material is several tens of square meter per grams, okay? Usually. For example, polyimide or cellulose acetate has about 20 square meter per gram. So per gram, you can only have about several tens of square meter in surface area. But the carbon, the carbon black has several hundred square meter per gram. So it's much more porous than of course, polymeric material. Now, in this MOF, I've seen that, perhaps that's the last year's data in my mind, that was about several 8,500, something like that, square meter per gram. So every time when they published their paper in top journal, yes, their surface area is from 1,000 to 2,000, 2,000 to 3,000 or 4,000 in Nature. And next paper might be, by changing something, you can make a lot of surface areas. So that they made some breakthroughs for the last 10 years. Anyway, you can make the zeolitic structure. You can make the organic framework rather than inorganic and organic framework, called the PAF, polymeric polymer organic framework, polymer aromatic framework, PAF, and it's 100% organic framework. Or you can make a covalent organic framework, okay? The COP, PUF, GIF, MUF, anything that makes some kind of framework, and you can change your the chemical elements. That way, I think a lot of people have made the very microporous materials. If you can make this geolytic the structure as well as MUF structure, because of the high microporosity, you can use this MUF or GIF or whatever by itself as a membrane material. But if you can mix this microporous inorganic material or organic material with the conventional polymeric structure, you can combine this together and utilize those microporosity of those materials into the non-porous conventional polymer and make the mixed matrix membrane called MMM or composite membrane or whatever you call, non-composite membrane, so that you can improve your performance of your conventional polymeric membranes. And the reason why they put this together is that you can improve your processability of inorganic material and improve the performance compared with the conventional polymer. So you can make a mixed matrix membrane out of this geolite as well. This is one of the structure. So as you can see, we have pretty, looks like a balls. Okay? It's a framework that you have seen here, and this framework was connected to each other and formed the pores. This pore size might be because of the crystalline structure. You have a porous structure inside. This porous X, Y, and Z, the dimension might be, counted, so that they can say that, well, the dimension or diameter of this pore, it might be 4 Armstrong, 5 Armstrong, 6 Armstrong, depending upon how they make this geolite structure. So about 2 years ago, the professor at chemistry department at Seogang University, Professor Yoon Kyung-byung, reported the geolite structure in Science paper in December issue of 2012. And what they have done was that they made this geolite with a very fine structure. The diameter was about 6 Armstrong, so that they can separate the benzene from cyclohexane. The difference is not that high. The cyclohexane has about 6.2. Benzene has kinetic diameter of about 5.8. So there is only about maybe 10% difference in between those two materials. And they reported in that paper the separation ability of the geolite they built, because they have a very fine structure, fine porosities and so on. Anyway, the smallest pore that I have seen in the geolite structure is coming as low as maybe 3.5 Armstrong, so that you can separate even the CO2 in the case. Anyway, if you have a highly porous structure in those geolites, you can utilize those microporous structure to absorb something, absorb gases, absorb chemicals, and then so that those absorbed material could be reacted later on after moving to the reactors and so on. Now, although you can make the rocks, you can get the rocks from the nature made of this geolite. We wanted to make a membrane rather than rocks, right? Although you have a chemical structure, we have to make this in a very thin film. I mean, very thin film, less than 1 micrometer, because if it's thick enough, although we have some separation, but the separation rate is not that high, so that we cannot use this as a membrane. So we have to make a very thin membrane on top of some support and so on. Now, in the April issue of Science paper, Science magazine, there is a report on zeolite membrane, very thin zeolite membrane coated on top of the hollow fiber, and that was reported by Georgia Tech, Professor Senka and Professor Kors. And I think I will give you perhaps next time about the PDF file of the paper. Anyway, there was a nice paper that they can utilize those microporous hollow fiber structure, and they can make the geolytic structure using the gaseous phase, I believe, gaseous phase, so that they can just coat on top of it and just fill. Pore structure of the polymer was filled with the inorganic material. So that way you can make the large area membrane module out of this geolytic structure to separate the C3 and C4, propylene and propene, propane and propene, or butane and butene, stuff like that. So you can separate those materials. Anyway, there's a lot of advances in making the zeolite membranes. Preparation of zeolite membrane has been categorized in four ways. First of all, you have to treat the support. You have to have a support anyway, right? Because zeolite itself is, although it's microporous, if you use microporous, 200 micrometer, the thick membrane itself, then it will be very expensive. So what it is that you have a polymeric structure or inorganic or cheap inorganic structure as a support, and you coat on top of coat the zeolite on top of those support. So that you have to treat the support in the first stage, and then you can make the you can make the zeolite structure on top of the support, impregnate them, and eliminate any surface defect or small defects. In other words, you have to polish your surface of the zeolite structure or alumina structure and so on. So alumina that we have prepared before, alpha alumina was very cheap because it's made of aluminum hydroxide and aluminum oxide. Alpha alumina has a very highly porous structure, whereas if you put on top of the alpha alumina the gamma alumina, then your pore will be plugged, will be filled with the alpha alumina, the gamma alumina. Gamma alumina, although it has so the defect, there is no defect in the gamma alumina, and on top of the gamma alumina, I believe you can make you can put the zeolite on top of that in that case. So this is the process of making zeolite membrane. In some cases, they use the stainless steel as support, or they can, or of course the porous stainless steel, or they can use gamma alumina or alpha alumina, and make the membrane in this way. Now, so we can make the MOF, GIF. I haven't, described those preparation of GIF and MOF at this point, but you can make a zeolite membrane. You can make a very thin layer on top of inorganic or organic support. Now, this is the process to make the palladium membrane, okay, which is the metallic membrane in this case. Palladium is a very expensive metal, but it has been used as a hydrogen separation membrane, or it has been used as a catalyst for hydrogenation for a long time. So by using this the palladium or even platinum, you can separate the hydrogen from CO2 at high temperature. In this schematic, you can see the membrane in the middle, and on top of this membrane we have the hydrogen molecule and oxygen molecule and some water at high pressure. In this situation, this could be realized at IGCC process, where you have if you have a coal, this coal was reacted with a catalyst, so they can generate the hydrogen and CO2 and water at high temperature and high pressure. The pressure would be several tens of atmosphere, starting from 20 to 50 bar, and temperature would be ranging from 200 to about 800 degrees C. So it's a very high temperature and very high pressure. You can produce the hydrogen and CO2. The purpose of the making this the coal is to make the electricity. Okay, before making electricity and the the boiler, the fuel will be hydrogen instead of coal itself. Okay, so hydrogen should be separated from the mixture of hydrogen and CO2. If you can do that, the hydrogen will be collected and should be high purity hydrogen could be used as a fuel to boil the water and get the steam and move your turbine and get the electricity. So that's the way of making clean electricity from the coal. Okay? That's what we call the integrated gasification combined cycle, IGCC process. So through those IG process, in order to be IGCC process successful, we have to have efficient separation at high temperature using this palladium membrane. So the palladium membrane, because it's a metallic membrane, you don't have any pore. You don't have any pore. So the reason why the hydrogen is separated from the mixture of CO2 and the water will be the ionic transport mechanism rather than porous mechanism. So the proton, you have a hydrogen molecule. It could become the hydrogen ion, and only the electron and the the proton will be transported. Proton, in other words, it loses your electrons. The proton will be transported and becomes the molecules. In this way, I think we have another slide to show this exact mechanisms of ITM. But anyway, the molecular ion transport mechanism is prevailing in these palladium membrane systems. So when we separate the hydrogen from coal or from water, if you think about water, we have hydrogen and oxygen. Okay? If you have efficient energy to separate the water, the hydrogen from water and hydrogen from oxygen, if your source of hydrogen is water, that is much efficient and much versatile process, of course. But we do not have the right process, right economic process to make the hydrogen from water at this point. Okay? Anyway, perhaps in the future, perhaps you will do that in separating the hydrogen from water. And if you get the hydrogen from water, then the hydrogen fuel cell vehicle called the polymer electrolyte fuel cell, polymer electrolyte membrane fuel cell will be realized in the near future. I think September 12th issue, about 3 weeks ago, issue of the science paper reports about the efficient production of hydrogen from water from the UK group. So please take a look at it if you're interested about the about hydrogen production. Anyway, if we can make efficient hydrogen from dirt, coal, or even water, then of course the hydrogen economy will be realized in the near future. So palladium or palladium alloys are regarded as the most important material for this hydrogen production. If you have any other membrane that is much more cheaper in production of the hydrogen production, then you will be the champion in this market. If you change your alloy components and have a high efficient, high performance, yes, that will deserve publication in the journals. This is an example of the membrane system. The palladium or palladium membrane has a very high hydrogen permeability, but the issue is that how thin that you can make your membrane on top of your support is an issue, and in some cases you can coat the inorganic. You can coat your palladium or palladium alloy on top of your gamma alumina, on top of your metals, stainless steel, porous steel stuff, and so on. And of course, it will be very expensive. But inorganic or metallic support is an essential part because, as you have seen, the high temperature, several hundred degrees C, several tens of a bar or atmospheric pressure is necessary during those processing of hydrogen production. Okay, almost the last part is about the membrane preparation is on the liquid membrane. Actually, liquid membrane was reported in 1967 as I think I have shown you in the history of membrane science about the science papers, and there was perhaps the second paper about the membrane in Science Journal, and they have done they have put the fixed carrier on the liquid stages so that some of the gases will be dissolved and reacted in the fixed sites as a carrier, and then transported through the liquid membrane. That's what we call the facilitated transport membrane. But anyway, liquid, they utilize the liquid phase as a separating layer rather than solid state. Now, they don't have any support in this case, or they may have some support. Okay? Liquid membrane itself uses the liquid phase as a separating layer, whereas a supported liquid membrane, SLM, supported liquid membrane, is the one that you have a microporous support, whether it's organic or inorganic, and those pore is filled with the liquid, and you can manipulate them in many ways. So this is much more mobile than the liquid phase itself. In our journal, we no longer publish the liquid membrane in Journal of Membrane Science because we think that you can separate something from liquid membrane, but we are concerned about the solid phase membrane as a real membrane. Okay? So SLM could be regarded in JMS, but liquid membrane, we wanted to move this to article to some separation journals, separation and purification technology and so on. Anyway, we have a liquid phase, and in some cases contain some carriers to transport some components. Usually, a liquid membrane has been used to remove the hazardous hazardous metals in wastewater. Okay? In the wastewater, it contains a lot of heavy metals, hazardous heavy metals like lead or chrome, something like that, and they could be removed selectively through these liquid membranes. And in some countries, they still use this liquid membrane technology, but because of the less flexibility of the system, it's not very common. But we can use this solid SLM, supported liquid membrane, as an alternative. So this is this SLM picture. SLM has a microporous membrane, and this pore was filled with liquid, and you can use the separation from the two faces. Whereas the emulsion membrane is the one that you make an emulsion, and inside of your emulsion you have some reactive phases in the liquid phase, so that some of those metals could be reacted in the emulsion stages. The last topic that I wanted to mention is about the ion exchange membranes. Ion exchange membranes have ionic structures, of course. It could have an anion or a cation, depending on the structures, positive ion or negative ions. Cation exchange membrane exchanges cations. Okay? Anion exchange membrane exchanges anions. So cation exchange membrane, although name is cation, it doesn't have any cations in the membrane, okay? Because it exchanges the cations. So cation exchange membrane should have negatively charged ion in the membrane, such as the sulfate, whereas anion exchange membrane has a fixed cation, like ammoniums, so that you can exchange the anion through those the fixed cations. Now, in this picture, we have an ion, such as a sulfate, sulfonic acid, so that only the interaction with this anion is a positively charged mobile ion, so that the cation will be exchanged anyway, will be moved from one to the other. How we can make this ion exchange membrane? Well, if you have the sulfate ion or ammonium ion containing functional groups into your backbone or into your side chain, then you can make this ion exchange membrane. Now the counter ion is sometimes called the quion, counter ion or Jupiter ion, could be moved anyway, and depending upon the type of those cation or anion or coions, your mobility is quite different, and the solubility of your membrane is quite different. Okay? You can have a proton form, you can have a sodium form, you can have a cation, the calcium form or something like that. And also, instead of a monovalent ion, if you have a bivalent ion, okay, bivalent ion, you can make the cross-linked structure. And the color changes depending upon your counter ions, such as if you have a cobalt, if you have iron, a ferrous ion, all the color changes. Now, this ion exchange membrane should have selectivity, and selectivity should be high enough to separate the ions. you should have resistance, electrical resistance. We need to have a membrane with high mechanical strength and chemical strength. And that's the essential part of this ion exchange membranes. These are the examples of fixed anions and fixed cations. Usually the sulfate ion or sulfonic acid or carboxylic acid, phosphorus acid are most interesting and most popular the fixed anions in this case CAM or CEM. In AEM we have ammonium, or in some cases guanidinium. Many of the other functional groups that could be presented will be used anyway in this case. We can make a homogeneous membrane or heterogeneous membrane. Homogeneous membrane, rather than homogeneous membrane, the heterogeneous membrane preparation is much easier. However, the homogeneous membrane is much more efficient in many cases. This is one example of making the CEM. We start from polystyrene. We have a styrene monomer. We have a divinyl benzene. Divinyl benzene has two vinyl groups, whereas styrene has one vinyl group. If we have only the one styrene monomer, the one vinyl monomer, we can make a polystyrene because of the vinyl polymerization and the radical polymerization or ionic polymerization, whatever you call, and make the polymer polystyrenes. But if you have a tetrafunctional, instead of bifunctional vinyl group, if you have a tetrafunctional DVB, then the extra vinyl group will act as a crosslinker, so that you can make a cross-linked structures. So you have the benzene main structure. The styrene main structure, and you have cross-linked structure. This could be linked together. This could be linked together. Okay, linked together. And after making the cross-linked structure, if you put this polymeric hydrogel into the sulfuric acid, then you can make this sulfonated structure, because the sulfonic acid is ortho and para attracting group. So sulfonic acid can go only ortho or para in this benzene ring structures. And by controlling those time and temperature, you can have specifically directed to the para positions ones. In this case, the sulfonic acid, if you put the sulfonic acid group in this polystyrene cross-linked structure, it will be much more swollen in water. Whereas if you do not have any sulfonic acid groups, it's not swollen because most of them are hydrophobic. If you put the sulfonic acid after sulfonation, then you have a swollen structure. If you don't have any cross-linked structure without having this divinyl benzene, you can form what? Water-soluble polystyrene. Okay, without divinyl benzene. But if you put divinyl benzene, because of a cross-linked network, you can form water-swollen gel. This is another example of making the AEM, anion exchange membrane, containing tetramethylene group or trimethyl ammonium group in here. First of all, usually they have to get, in this case, the methylene chloride here on the para position 1. So you should have, the ethoxymethane here as a reacting group, and form the methylene chloride in the para position 1. And if you can replace this with the triethylamine, then you can form the triethylamine containing the AEM in this case, because you have a positively charged fixed charged one you can move this anion so that this is called the anion exchange membrane. Well, so far we have seen the aliphatic groups containing polymer, but we can have an aromatic group containing polymer. Many years ago, they were making the heterogeneous type of this sulfonated polymer. In this case, this is a polyether-ether ketone, called a PEEK, P-E-E-K. But after sulfonation, you can make the sulfonated polyether ketone called S-PEEK. But sulfonation requires the heterogeneity of the sulfonated polymer S-PEEK. What it means is that if you have your PEEK in the form of powder or in the form of film, and if you put those powder or film into a sulfonating medium, then the reaction will occur from the surface of powder or films. It may not go directly into the core or very deep side of your film or in the powder. So after reaction and washing and removing everything, you may have a still unreacted part of your the powder or films of your PEEK. So that's what we call heterogeneous reaction. Whereas if you dissolve your polymer into a liquid phase and have a reaction, then that's what we call the homogeneous reactions. Homogeneous reaction is quite difficult in this case because we have to use the aqueous phase, whereas this PEEK is not soluble in the aqueous phase, soluble in only the organic phase, and it's not miscible at all. So heterogeneous reaction is not possible, and only the homogeneous reaction is not possible, and heterogeneous reaction causes some unreacted PEEK. So though the yield of this S-PEEK was not what we have expected. So instead of this post-treatment of PEEK, when we have a sulfonated monomer in the stage of making the PEEK, we can just directly go from there. In other words, if you have a styrene containing monomer, styrene with the styrene and styrene with the sulfonic acid, sulfonic acid containing styrene reacting together with the divinyl benzene and can make this process. We can eliminate this sulfonation process, right, by adding the sulfonated polymer. For the same analogy, we can make the sulfonated PEEK by reacting sulfonated monomer in the preparation of those PEEK. So we can eliminate this process. Now this is possible starting from for the last 2 decades. For the last almost 2 decades, it was possible. So we can easily make the S-PEEK these days, or sulfonated polyimide, sulfonated polyaldehyde methysulfone, sulfonated polybenzimidazole. Many of those aromatic polymers containing sulfonic acid could be directly synthesized in the laboratory and in some scale, larger scales at all. PEEK was originally produced in UK by ICI, the company called ICI, and also in China, near Changchun. And they right now China is producing this PEEK and S-PEEK at all, also in China. But originally in the literature there was a report that this PEEK was produced by ICI a long time ago, and perhaps you can take a look at those the production scale of this PEEK. This is an example of another ion exchange membrane containing sulfones. This is the ether ether sulfone. Okay, this backbone is aromatic sulfone. This could be easily made by reacting the sulfone containing the hydroxide with the bisphenol A containing hydroxyl group in here. So if you have this block, this monomer and this monomer, we can react together to remove those HCl and can make these iron ether sulfones. Now this is the backbone, and in that reaction we can put those the quaternary salts. This is what we call the bicyclic octane containing the diazo groups, and the tertiary group could be acting as the anion exchange the membrane as a crosslinker. So this polysulfone is very stable, whereas the side group is acting as a functional groups in making the ion exchange membranes. Naphthalene is a representative ion exchange membrane in this case. The backbone is backbone is composed of carbon and fluorine atoms, so it's more like a Teflon, whereas you have a side chain here, which is different from Teflon. This side chain is made of the aliphatic, the perfluorinated ether group containing ones, and at the end of your side chain we have a sulfonic acid group in many cases, and the length of this M and N is different depending upon the manufacturers. Naphthalene has the longest side chain, whereas 3M made a little shorter one, and also Solvay manufactured a little shorter one too. So if you have a long chain and a short chain, your mobility of your sulfonic acid group is a little different. Okay? And the mechanical strength, although chemical stability is a little different. So recently, the other two companies that I mentioned manufacture a little shorter side chain group containing sulfonic acid groups, and that means that they can control this M and N. Okay? This naphthalene was first introduced in the 1970s. And this film is transparent, and it's very stable. It's very stable. It's not dissolved in any organic solvent, or it absorbs the water, and chemically stable because we have it's like a Teflon units, but it has a sulfonic acid group, so it can attract the water. And the water channel is about 25 nanometer in those channels, and you can see a lot of schematics of naphthalene microstructures. Because of the chemical stability and ion exchange capability, it has been used as an polymer electrolyte membrane fuel cell, the membranes for the PMFC, and that was first used in the fuel cell in the satellites, the space shuttle. Okay? So they can make the water, they can get the power from this PMFC using the water as a hydrogen source in the space, because they cannot carry those water. They should make the water and can generate the electricity using the hydrogen as a fuel, and the hydrogen fuel using this hydrogen fuel cell. Okay? Of course, you can get the energy from the solar sources at the time, and so on. So it was very expensive. But right now, for the last 50 years, There has been a lot of production, and this naphthalene has been used to make the direct methanol fuel cell. For although it has a little bit of a problem about the methanol crossover, but anyway, they can use this naphthalene in DMFC, and can be used in the vehicle. But it's not automobile, not the passenger car, but it could be a 뭐라 그러지 저기 lift kind of lifter. Okay, you can operate your lift, not that elevator, but to move your luggages from one place to the other in the cargo system. You can make those vehicle or lift using this direct methanol fuel cell in Germany. They can commercialize this in the case. Fuel cell vehicle, 100% fuel cell vehicle is operated here in Korea, South Korea. About 10 years about 10 years ago. Right now, I think several hundred, at least several hundred, maybe several thousand. The fuel cell vehicle is moving right now as a pilot vehicle, and the Hyundai Automobile is targeting in 2015 to make this the fuel cell vehicle. The number of those vehicles will be about, I think it's about 10,000 by the year 2015, and by the year 2020, maybe several, hundred thousands, up to about 1 million vehicles. They forecast that this fuel cell vehicle market share will be maybe few percent of out of their electrical vehicle. The vehicle, and the rest, and also it could match with the electrical vehicles. So electrical vehicle or the fuel cell vehicle has some market share. Electrical vehicle using this naphthalene or other hydrocarbon membrane is one of the issue among the automobile manufacturers, particularly in Japanese and the Germans, and of course Korean. And the membrane so far is naphthalene as a promising one. Or of course you can have the other alternatives by changing the side chains from the other producers in this case. Okay, so if we can wrap up what we have talked about. So the rest of the slides are the wrap up of the membrane preparation. So we can think about the materials. Well, I've talked to you about the sulfones, sulfonated sulfones. I've talked to you about the polysulfones. If you have functional groups containing sulfonic acid, whereas if you do not have any sulfonic acid group, we have different applications. Polysulfones versus the sulfonated polysulfones are quite different because of the nature of the philicity and phobicity. Polysulfone is hydrophobic, whereas the sulfonated polysulfone is hydrophilic. You can make the polysulfone as a hollow fiber, but it's very difficult to make hollow fiber out of the sulfonated polysulfone because it's water soluble. Okay, it's not water soluble, but it's organic soluble. So the process might be a little different. Polyamides are hydrophilic. If you put the polyvinyl pyrrolidone in polysulfone, yes, you can make hydrophilicity. Polyvinyl alcohol is a water-soluble polymer, but if you cross-link them, polyvinyl alcohol is water-soluble at 80 degrees C, little hot water, okay? Not at room temperature water. Although it can absorb the water, It's not soluble at room temperature, but if you boil them, it will be soluble. But if you cross-link them, you can make a gel. You can make a hydrogel out of this cross-linked polyvinyl alcohol. Polyvinyl alcohol can have phelicity because of hydroxyl groups in the backbone, in the side chain, so that it can have interaction with the water. Now, Sulzer uses this PVA membrane in removing the water, from the ethanol. Okay. So when they use this PVA as a very thin membrane, they can use this membrane for the process called evaporation. So if you have a hot ethanol solution in the feed, and you have crossing the PVA membrane has a much more solubility and interaction with the water rather than ethanol. Okay, so the water vapor or hot water will be moved from feed to the permeate, so you can concentrate your ethanol. Now, it's not economical to remove large amount of water in your aqueous ethanol solution. Okay? It's much more economical at high ethanol concentration. And if you have a small amount of water, you can selectively remove your water through this cross-linked PVA membrane. Okay? So in evaporation process, there is a azeotropic mixture formed at 95.5 weight percent ethanol. Okay? In other words, if you have a composition of ethanol from 0 to 100%, we have a distillation curves. Distillation curves looks something like this. And these are the azeotropic line. Okay? Now this point is about 0.995, 0.955. And what it is that if you feed in the distillation column 10% ethanol, you can obtain maybe 20% ethanol. So higher ethanol concentration is expected up to about 95.5%. But at 95.5% ethanol, okay, as a feed, you cannot obtain higher than 95.5% ethanol, although you put a lot of energy. It just stops there, formed because of the formation of azeotropes. Now, in industry, they still can make the 99.9% highly, absolute ethanol by breaking this azeotrope point, by adding benzene as an azeotropic breaking components. So if you add a small amount of benzene in ethanol, aqueous solution at a high concentration, yes, you can break them and can go up to about absolute alcohol. However, you still can contain a little bit of benzene, and if you drink your benzene, what happened? What's going to happen? Although it's a small amount, it's a carcinogenic, so it's not feasible. And if you can start from 9%, so you have a 9% ethanol, and maybe 10% water, or maybe 93% ethanol and 7% water. And as a feed, this will be the feed. If you have a membrane and can selectively remove a small component, water, through here, and can concentrate in the retentate as an ethanol. And that's what they call the evaporation. So evaporation unit, along with the distillation column in the ethanol production at the production line, the pulp evaporation membrane can be used to move 90% to 96% in the so you can just take it out. So this is the commercially available process for evaporation. PVDF has been, largely used. PDMS, which is the polydimethylsiloxane silicone rubber, and so. We can have a composite membrane, polyester matrix, polyacrylonitrile support layer, PDMS, the coated layer are the most important thing in this case. Depending on the organic mixture using pulp evaporation, the pulp evaporation process it can be used to make the bioethanol production, as you can see here in that example. But if we have a mixture of organics, such as cyclohexane and hexanone, or normal propanol and heptane, or hexane and methanol, or cyclohexanol and methanol, and so on. You can use many of those membranes. You can even use pulp evaporation to remove the benzene and hexane. You can use those pulp evaporation to remove NMP in the aqueous solution, DMF from aqueous solution. Methanol with the MTBE. MTBE is octane booster. Methyl tertiary butyl ether is MTBE is the abbreviation of the methyl tertiary butyl ether, and that could be used as an octane booster. Okay? So they add a small amount of MTBE in gasoline, and during those manufacturing process, you have to contain methanol with MTBE, and it forms the azeotrope, of course. So azeotrope requires a lot of energy to break those azeotropic points, and pulp evaporation process can be used to break those azeotrope, and you can save the energy. Now, selectivity and permeability or permeance is quite important. Of course, the higher the better. Yeah, methanol and MTBE, and benzene and xylene. There's hundreds of, more than hundreds of, published articles about what's going on. You can use a polymeric membrane or inorganic membrane, depending upon what you're going to do. Inorganic membranes are difficult to fabricate, but it's not impossible. So zeolite membrane has been used to produce this zeolite ethanol production in Brazil. In Brazil, you have a lot of the biological resources, such as corn, and by fermentation, you can produce the ethanol, and this ethanol from the biological medium in the aqueous phase should be removed and to concentrate to make the bioethanol. So in Brazil, this pulp evaporation unit is very much required. Of course, in the U.S., they're very keen to use this bioethanol as a fuel. In Southeast Asia, they're, of course, very much interested about the bioethanol production because they have a lot of waste, bio waste, coconut oil production. You have a lot of cellulosic stuff, and if you can make the very efficient bioethanol production using this membrane, of course, membrane process, yes, you can be possible. So, Japanese manufacturer used ZSM5 in a very thin form and make a plate and frame type of membrane, and was installed in Brazil. And I forgot about the production scale, but it's a huge scale, and the inorganic membrane for the evaporation is operating right now in Brazil. RO, NF, and all those membranes used, of course. Polybenzimidazoles, very interesting material. It could be operated at high temperature. Polyethylene oxide, same as polyethylene glycol, is used to capture the CO2 in many cases. PTMSP, so-so. I think it's, although it's highly permeable polymer, it's interesting, but not very widely used in these days. So with that, I think I can just stop here, and we can talk about the characterization, how we can characterize the pore, how we can characterize the other properties of the membranes. Will be touched perhaps next week. So far, we have talked about the materials for membranes and how we can prepare the membrane. So in summary, the membrane is not just a film, but it could be a very thin film or very thin layer to separate something, from the mixture. And we need two very important parameters. One is the selectivity, okay, from the mixture, and the rate of the permeation, rate of permeation. How fast you can remove your component from the mixture is regarded as a very important parameter as well. So polymers, inorganics, metals can be utilized to make the membrane, and depending upon the application, depending upon the process, you can choose your material for the specific cases. I did not touch about the nanofiltration, particularly SLN, but I hope that in the future we can touch those. So from next week, I think we can go to chapter 3 about the characterization of the membranes, and I'll send you the PDF file right now. Any questions or comments? If not, then I think we'll see you on next Wednesday. Thank you.